Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss the concept of steady state stability, and in inspecting the steady state stability, we will consider a generator connected to a motor, and in between there is a transmission line. The voltage at the generator side is EG, and the generator internal reactance is XG. The motor is running at a voltage of EM, and the internal reactance of the motor is XM. And we know that the internal circuit of a generator and motor is composed of windings. So the overall nature of the internal circuit of generators and motors can be represented by the inductive reactances, and in between there is a transmission line, and we have ignored the resistance of the transmission line, and only the inductance of the transmission line is considered, which is specified as Xe. So in this case, the current flowing between the generator and the motor I will be equal to Eg minus Em divided by Jx, and X is the total reactance of the system. Okay, so X is equal to Xg plus Xe plus Xm. So power delivered to the motor by the generator is equal to the real part of E times I conjugate, and E is equal to Eg. Okay, this is the applied voltage or the generator voltage, and the angle of this generator voltage is taken as delta. The I vector is equal to Eg minus Em divided by Jx. But when we are dealing with complex powers, it will be I conjugate, or we can write the power as the real part of E conjugate multiplied by I. So both expressions will yield the same result. Either we can use E conjugate into I or E times I conjugate. So I conjugate is equal to Eg with Eg conjugate minus Em conjugate divided by Jx conjugate. So Eg is equal to Eg with an angle of delta, so its conjugate will be equal to Eg with an angle of minus delta. And Em, the motor voltage, is taken as the reference, so it is lying at the x-axis, and the phase angle of this Em is equal to 0 because it is lying at the x-axis. So Em with an angle of 0, and its conjugate will also be equal to Em with an angle of 0. So Jx can be written as x with an angle of 90 degrees, and its conjugate will be equal to x with an angle of minus 90 degrees. And the phasor representation of all these vectors is presented in this phasor diagram. And here you can see Eg is leading Em by an angle of delta, and Em is our reference, which is the motor voltage or the load voltage, and the current flowing through Em or current flowing through the motor will be lagging behind the motor voltage by an angle of alpha, because this is an inductive circuit, so current will be lagging behind the voltage. So this is our Em, and this is the voltage drop across all the inductive components. So that is equal to Ix, and the vector sum of Em and Ix will be equal to Eg according to this expression. So Eg is equal to Em plus Jix. So their vector sum will be equal to Eg, and this is the angle delta of Eg. Em has zero angle, and I is lagging behind Em by an angle of alpha. So let's simplify this expression. So we will evaluate the real part of E this times this. So Eg with an angle of delta multiplied by Eg with an angle of minus delta will be equal to Eg square. Delta minus delta will be equal to 0. And in the denominator we will have x, and that minus 90 when placed at the top will be equal to plus 90. So Eg square divided by x with an angle of 90 degrees. This is our first term, and minus Eg multiplied by Em with an angle of delta plus 90 degrees. So this 90 will be added when it goes to the denominator, and it will be added to delta, and x will be in the denominator. So when this angle goes to the numerator, it will be plus 90 degrees. So let's simplify these polar expressions to rectangular form. So this will be equal to cos 90 plus j sin 90, and this angle will be equal to cos delta plus 90 plus j sin delta plus 90. So the real part will be equal to cos 90, and the real part of this term will be equal to Eg Em over x cos delta plus 90. So here cos 90 is equal to 0, and cos delta plus 90 is equal to minus sin delta. So it will be equal to Eg Em over x sin delta. So this is the expression of power as a function of the angle delta, and this is called power angle equation. And here the maximum power is equal to Egem over x. So the power will be maximum when delta is equal to 90 degrees or sine delta is equal to 1. So P max is equal to Egem over x, and we can write P equal to P max sine delta. So this is P max, and we can take the derivative of this power P. So the derivative of this power dP over d delta is equal to Egem over x cos delta, and this derivative term is called synchronizing power coefficient or stiffness. And we can plot this power and this synchronizing power coefficient on top of each other. This is our power. This is the maximum value at an angle of 90 degrees, and at the angle of 0 and 180 degree, the powers are equal to 0. Similarly, this is the plot of the derivative of power or synchronizing power coefficient, and it is equal to Eg Em over x cos delta. So it will start from here, and at 90 degrees, this derivative term will be equal to 0. So dP over d delta must be positive for stable operation. So the steady state stability will be ensured if we have positive values of dP over d delta. So if the power system is working in this regime, when dP over d delta is positive, then the system is said to be in stable mode. Otherwise, if the system is operating in the second half, the derivative term will be negative, and the system will be operating in the unstable region. So this is the stable region. Okay, this is the plot of P, this is the plot of dP over d delta. This is the stable region, and after this point, dP over d delta is negative, so that will be the unstable region. So that is all about the concept of a steady state stability, and I hope you have understood the steady state stability concept of a power system. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.